Good afternoon, everyone. Sajid sir, shall we start?
Yes, ma'am, you can start.
Yeah, okay. I'm audible, na? So, good afternoon, everyone. Myself, I'm Dr. Hetal Mehta. It's my pleasure to extend a cheerful welcome to you all. Friends, we are moving ahead today with the day 5 session of the 6-day National Symposium on Scope and Prospects of Chemical Science. And it is indeed gratifying to note that the topic of today's talk is an attempt made to disclose that stream of science which has successfully changed the vision of researchers and scientists. This stream says, stop looking at big things for a while and please look at the small, tiny things, because someone truly said that there's a plenty of room at the bottom. This field is loaded with immense potential and exciting technology that is helping to work on challenging problems of global importance. हम बोल सकते हैं like छोटा packet बड़ा धमाका. Yes, today we are going to have a brainstorming session on nanochemistry. And for today, the speaker is Dr. Vivek Paul Shettivar. Sir holds his doctoral degree from DRDE Gwalior. This was somewhere in the year 2005. That means 15 years back. Sir, I would like to mention here that there are many students, especially at BSc level, who are always worried how many years we need to dedicate to get a PhD. PhD जरूरी भी है क्या? कितने साल लगेंगे? And the biggest doubt is there any scope in research? I think today they can get the answers to this question. Sir's journey did not end with his PhD, but we can say it was just a start. Immediately after completing his doctoral degree, he flied overseas and did his postdoctoral research in France. After this, he has worked with some of the topmost research institutes in USA, Coast University in Saudi Arabia. Sir has got an exhaustive list of fellowships and awards, because of which he has made my job difficult to introduce him in 3 minutes. I'm not exaggerating at all. In the last 20 years of his journey in research, he is awarded with at least more than 25 awards and fellowships. To name a few, Young Scientist Award in Germany in 2012. His dedication and crave for research has always remained at the peak, because of which Sir was among the top 25 cited authors in Tetrahedron Journal in 2010-11. From this, we can understand the type and number of research publication he owns. Sir has been selected as one of the 175 faces of chemistry worldwide by Royal Society of Chemistry. And see the situation in 2009. Sir was offered with Helmholtz and Marie Curie Fellowship, but Sir did not accept them because he had his prior commitment to Coast University. Sir is the winner of Bronze Medal. He had received from Chemical Research Society of India and many more. One more important I would like to mention is Sir has got the Asian Rising Stars Award at Singapore, and that too from Nobel laureate Professor Negish. इसके बाद, if we see, apart from his outstanding research record, he has proved himself as an excellent teacher. Sir has added immense value not only in his research field, but also to the lives of so many students he has taught and mentored over the years. And recently, Sir had one more feather over his crop. We are happy to hear that Nanovision Department of Science and Technology from Government of India has awarded Sir with prestigious Young Career Award in Nanoscience and Technology. We congratulate you, Sir. We are grateful that Dr. Vivek Sir has accepted our invitation to be the part of this elite event. It is truly our privilege to listen him, and I can say that we are all in for a treat today. Just two instructions for our dear participants. Question answer session will be taken at the end, and participants can post all their questions in Telegram group. And please fill the feedback form properly within the given time. Sir, the session is all yours now. Thank you.
Yes, thank you, Dr. Mehta, for such a detailed introduction with nice pictures. I see my own thing in 2005 with mustache. So
Yes.
thank you very much, and thank you very much for inviting me to deliver this lecture. So let me share
Thank
the.
you.
Can you confirm that you are able to see my slides?
Yes, sir, we can see.
Okay, they're changing, right? Are the slides changing?
Yes, sir, yes.
Okay. So good afternoon, everyone. Today I'm going to talk about the role of nanochemistry to combat climate change, and I realized this particular uh, talk series is about to provide the information about the careers to, I hope, chemistry student, what should they do, whether if they study in chemistry, whether they will get a job. I think that's the underlining question that everyone is asking. And I think the climate change is going to provide that opportunity. You will see that if we really want to save planet Earth, if we really want to combat climate change, we need to develop a range of technologies, right? Whether to increase the energy efficiency of the existing process, or to find out alternative energy sources, right? Harvesting the solar energy, harvesting the wind energy, uh, or maybe then finding out the ways to develop the chemicals without producing CO2, or use of CO2 to produce different chemicals, right? So you will see, or use of CO2 to convert convert them into cements, plastics, uh, almost, and then lots of environmental issues that we are facing, and we will face more in coming times. So you will see that chemistry is going to play a extremely critical role in fighting the combat change by developing different materials and technology, and therefore I think there is a huge opportunity for chemists to really contribute in this direction. So I guess we all know about the climate change, and especially when there is a rain in Mumbai, snows, when several part of the Mumbai goes underwater, we know some of us at least try to connect that with the climate change. So today I'm going to talk about briefly the why there is the climate change, and then my uh, focus is on synthesis of nanomaterials, nanocatalysts to combat climate change. So I guess we all know that our energy source is sun energy, solar energy, right? There is some sort of a Earth energy budget. So you get energy from sun, some of that get reflected while it is reaching the Earth, and then a significant portion get absorbed by the Earth. And these, and then there is a secondary radiation by the Earth in the form of infrared radiation, which ideally majority of should go out, and some of that get absorbed by several gases, including CO2, because CO2 has ability to absorb the higher radiation. And that's why ideally there need to be CO2 so that some of the higher radiation, some of these secondary radiations get trapped, and we have this nice weather, nice temperature around us, and that's why we have a life on planet. But somehow now the concentration of CO2 increased dramatically. That means we are trapping more and more these infrared radiations, thermal radiations, you can say, and you are, because of that, you are increasing the temperature of the globe. You are warming the globe. So that's a typical chemistry behind the climate change. More the CO2 around the in the environment, more is the trapping of the secondary radiation, infrared radiation, which will warm the globe. And there are several other greenhouse gases, are the gases which traps these radiations. But CO2 is one of the stable molecule. It has a long lifetime in the environment, so that's why it causes the biggest harm in terms of the climate change impact or global warming impact index. Now you can see the way the CO2 was before, the pre-industrial era, which is up to 1950, and suddenly after 1950, when we started becoming more, artificial, our energy dependence was on fossil fuels and other sources which produces CO2. You can see suddenly the CO2 started increasing, and there is a sharp increase in the CO2 today. Not today, it's like last year I need to update this. So this is 1415 39, and it's even few 2-3 ppm more now currently. It's a huge amount of CO2 in the environment. Now, because of that, you see an increase in the temperature. This is average 11-year temperature, and you see with time from 1880 to 2000, you see an increase in the temperature of the planet, which is the global warming. Now, there are some people who say, oh, there is no climate change. This is all natural processes, and one of the argument is, since you are getting more solar energy now, that's why it is increasing. But you see now this blue curve is all about the solar irradiance, solar energy that we are getting, and it's nearly constant. But there is a global warming, clearly indicating that we are trapping more and more of that energy. We are not getting more of that energy, right? And then because of the global warming, the first thing that will happen is the ice, Arctic ice, sea ice, and everywhere will start melting. They're already melted. You see, the y-axis here is 7 millions of kilometers, a huge number in 1980, and now this data is up to 2015. You see, out of 7, we reach 3.5. So 50% of ice is already melted. So that's really a serious thing. And then, since ice is melting, uh, globe is warming, what will happen? The sea level will rise, right? And you see the data from 1880 to now 2017, a systematic increase in the sea level. So it's about 8 inches since the beginning of the 20th century. And this is a paper, recent paper, 2019, 2 years old. Obviously, this is a modeling, a theoretical paper, which says that if we continue the way we are, and if we continue producing the CO2, and if we don't stop emitting and start mitigating the CO2, sooner or later, several of the cities like Mumbai will be under the water. So you can imagine the seriousness. Not the climate change is not only impacting the environment, but it's also indirectly or directly impacting the health. There is a recent study where the NASA scientists discovered a bacteria in this Mexican mine, which is several million year old. And then when they tested the different antibiotics that we have, 18 top antibiotics, that bacteria was resistant to all of that. And this is very old, so we don't really know any information. We don't have any information about that bacteria, right? And we don't know how it behaves when it enters the human body. So imagine now we are struggling with the coronavirus. There were already viruses in the corona family, so there was some amount of scientific knowledge about the virus that helped us to come up with the vaccines, and we are trying to fight with it. But imagine a situation where we are infected by a virus or bacteria, which is million-year old, several million years old, and we have no information about that. And we will struggle to really to combat these bacteria and viruses. So that's another thing, right? There are diseases hidden in the ice, and they are waking up because of the global warming, because of the climate change. So now the question is it too late to stop the climate change, or the chemist, what is the role of a chemist to stop the climate change? I don't know whether it's too late or not. That's no one can tell. But I think as a scientist, as the students of the chemistry, we should find out a way to combat the climate change. And how do I do it? So obviously this is a huge problem, and science alone cannot really combat the climate change. If someone is saying, okay, I will develop some technology and that will help, that alone will combat the climate change. No, it will help us to combat the climate change. But I think there are several other things that we have to think about. One is the population, right? Obviously, if you have more and more people, we need more energy. You are going to use more and more fossil fuel. We are going to produce more and more CO2. So population control is the critical thing. And then the energy sources, how much energy use, how much energy I want to use, right? If I have a 10 tube lights in my hall, do I really need all of them, or can I just do it with 5 of them? I save 50% of the energy, right? So it's not about whether you are rich or poor, it's about the energy saving, irrespective of whether you can spend the money to put all the light on. So that's a more a behavioral change that we have to follow. And then the energy sources, right? Like most of the energy in India is still from coal and other carbon-based fuel, 70% of that, and that will produce huge amount of CO2. India is now, I think, third in a CO2 emitter. So can I use some other energy source like wind, solar energy is one of the best right now. So and then we have to use as much as possible the solar energy. At the same time, can we develop the technologies which allows us to do more work using the same energy, right? We know now the previous, those halogen lamps are the tube lights, and now the LED. It is low power. You need a lower energy, but it gives the same light, right? So, can we develop different technologies, improve the technology so that we can do more using the same amount of energy? So you are increasing the energy efficiency, right? So those are several things that one has to do. Uh, the cement industry produces large amount of CO2, one of the biggest CO2 emitter. Then now there are two solutions. We can ask cement industry to stop producing the cement. That seems impossible, right? We need a cement. We need a stainless steel is another industry who produces large amount of CO2. You need a stainless steel, right? We have so many people who need a home and other things. So they need cement and steel. So we cannot stop producing the cement and steel. But then can we find out a way where we produce the cement, steel, polymers, chemicals with a who produces less amount of CO2? Can I find out a way where I need lesser amount of energy to produce steel or CO2 or cement? So these are different ways by which one can combat the climate change. Now, more specific to the chemist, what chemist can do? Obviously, chemist can come up with a process which will convert CO2 to cement. I will show you some example. So I think the role of a chemist in the combating the climate change is, first, we should capture the CO2, because we know there are processes which cannot be stopped. The cement industry is going to produce, emit lots of CO2. So now, as a chemist, can I find out a way to capture the CO2? So that's the first thing. But we all know capturing and storing is not the best solution, because what do you do with those high amount of CO2? The storage will not be a permanent solution. So we need to find out a way where we capture the CO2 and then convert that CO2 into useful chemicals and fuels. In fact, think about this: that everything that you see around, right? Everything that is made up of a carbon, can that be made from the CO2? Right? Polymers, plastics, cement. Look everywhere. So even the concrete, everything, anything that requires the carbon, can that carbon come from the CO2 rather than the fossil fuels and other carbon sources? If that is possible, then this problem of climate change is solved. And you see now the role of a chemist here. When you are to find out a way to deal with the carbon, it's the chemistry's role, right? So that's how chemistry will able to combat the climate, contribute to combat the climate change, and that's what we do in TIFR. We are trying to develop different kinds of material to do this. So there are two ways. There are two things that we are doing in the lab. One is developing the material to just capture the CO2, and then the other project or other goal is to then convert the captured CO2 into some chemicals, say methane. The CNG gas that you fill in your car is 98% methane. So I don't need to then get the methane from fossil fuel, but I convert the CO2 into methane, right? So you are closing one inlet of the carbon source, and I'm using the waste CO2 to produce the energy, to produce the methane as an energy source. CO2 to ethanol, C2, C3, CO2 to cements, right? CO2 to polymer, CO2 to concrete. There are various ways of doing this, and it's chemistry. But there is a challenge. And challenge is, again, if you look at the basic chemistry, CO2 is one of the stable molecules. sp hybridized is linear molecule, very stable, right? Low energy. So why will CO2 convert into anything else? It's already achieved its stability, right? We know that generally the reaction goes the way you go to the lower energy side. Now, so conversion of CO2 will always need energy. It's a energetically unfavorable reaction, thermodynamically unfavorable reaction. Kinetics is also slow. So you need to put some energy, not some, large amount of energy to overcome that activation energy barrier and then react with CO2, H2 or alkenes or anything. And that is the basic fundamental challenge, that I need lots of energy to convert CO2 into useful chemicals. And then the idea now is I first reduce the energy required to do this conversion. And now how do I reduce the activation energy barrier? By using the catalyst, right? So I will show you some of the results where we are using nanomaterials to develop the catalyst, which will allow you to reduce the activation energy barrier, and you may able to then do the reaction at a lower temperature, maybe the room temperature. That's the dream, right? And even in several cases now you need energy, then there is a you need to connect this with the solar energy harvesting, where I will find a way, I will find a material or a chemical which will harvest the solar energy and give that energy to the CO2. And now solar energy is also free, CO2 is obviously in excess, so now entire thing becomes natural. So that's why this is sometimes it's called the artificial photosynthesis, where you are what trees are doing, taking CO2, water, sun's energy, and giving us the product. Now we have too much of CO2. We don't have a space to plant more and more trees. We should plant as many trees as we can, but there are theories and there are studies, and we also know there is a limited space. So we can't really dependent on planting the trees. That will not solve the problem. So we need to create artificial trees which will do the same thing, harvest the solar light, capture CO2, activate the CO2, split the water into hydrogen, and they together react to get you alcohols, carboxylic acid, esters, polymers, even one day glucose and other foods. So now if you look at these, and there are people who think that the CO2 conversion will never solve the climate change problem, because you see here, you need to put lots of energy. My personal idea is, yes, it needs energy and there is no way out. I can reduce the energy, but you will always need the energy. But we know that there is a huge amount of solar energy, and we also learn to harvest the solar energy, in the form of electrons or heat or electron as electricity, and we can use that, right? So I don't see energy as a problem. What I see is the catalyst development still under the research level, and the inspiration can be from this particular reaction, Haber-Bosch ammonia synthesis. In 1909, if you ask, I want to convert nitrogen, which is one of the stable molecule, even more stable than CO2, and if you say I want to convert nitrogen into ammonia, everyone will laugh at you. But see Haber. Haber came up with a process where he reacted nitrogen with H2, and he was able to convert nitrogen into ammonia. Right? That was a breakthrough. Now, if you look at the process, the catalytic process, you will see that he used 100 bars of the pressure, huge pressure, 400 to 500 degrees Celsius as a reaction temperature, again very high, and osmium, one of the radioactive material, as a catalyst. So even he was able to do something, then again the engineer will say, they must have said, this particular process can never be commercialized. This is extremely the reaction conditions are extremely tough, that you will never able to commercialize. But then Haber made Bosch, a scientist from BASF, an engineer, chemical engineer, and he developed reactors which allowed them together to really commercialize this process, a process which seems impossible, nearly impossible. Nitrogen is very stable molecule, needs high amount of energy. But they were able to not only make this breakthrough discovery, which both of them got a Nobel Prize for this, but they also commercialized this in 1913, just 4 or 5 years. And now, whatever the food that you are eating without Haber-Bosch, you will not able to get that food. 2/3 of the amount of food that we get is because of Haber-Bosch process. It's because of the ammonia. Ammonia gives you the fertilizers, and we all know only after fertilizers came in, we were able to increase the yield of our farming and able to provide the food to all this growing population. So this particular reaction, at least for me, is a inspiration. If nitrogen can be reacted and ammonia can be produced at a commercial scale, CO2 is far more reactive than nitrogen. So ideally, it should be possible, and you will see in next 4 or 5 years, the person who does this commercial level will be the Nobel Prize winner. So this is where the chemist can play a role. Then how do I do it? How do I achieve it? Again, it's the catalytic process. So I need to develop a catalyst which can do that. And catalyst, in my case, is a heterogeneous catalyst. where you need to develop different kinds of materials. And I will show you that how do I tune the properties of the material so that I can tune the catalytic activity of that material. So tuning of the properties can be achieved by tuning the particle size of the nanoparticles, the shape of the nanoparticles, morphology of the nanoparticles. So nano science and nanochemistry gives you these handles to tune the properties of the material by simply changing their size, shape, morphology, say some defects or interfaces, and using that one day we will be able to really make a produce a process which is commercially viable. So now I will start with my technical talk, where I will give you some example of how do we really develop these technologies to convert and capture and convert CO2. So either you want to capture the CO2 or you want to convert the CO2 by some catalytic process. Uh, if you one thing that you need is a high surface area material, obviously for a heterogeneous system, where you take this high surface area material. Now CO2 is bit acidic, so I make my surface a basic, it's simple acid base chemistry, and you capture all the CO2. And then if surface area is high, then your interaction of the CO2 molecule with the basic sites will be more, and you will be able to capture more and more CO2 faster and faster in terms of kinetics. And same will be true with the in terms of catalysis, right? You will have a better diffusion, better interaction of the reactants with the active site, which is spread over the surface, and you will be able to do faster and more efficient catalysis. So in our lab, we developed this high surface area material. This is called nanosilica, which is the which has this dendritic fibrous morphology, and that's why we call them BFNS. One can tune the particle size, say from 50 to 100, 100 to 200, 400 to 600. You can get a different particle size ranges. It has high surface area. 500 meters square gram is like if you take a 1 gram of a powder in your hand, it's like a 1 football ground. So huge surface area, and you can use that to generate active sites onto that surface, or some other basic sites, acidic site, hydrophobic, hydrophilic, and do different functions using that material. It has excellent thermal and hydrothermal stability, mechanical stability, so that I can do high temperature, high pressure processes, and it's easy to synthesize. Of course, when we discovered, it was very complex to make, but now we recently wrote this nature protocol where we gave a stepwise synthesis, including the videos and stepwise how to synthesize it. Any lab, even which has a heater and mixer, that's the only thing need, and a non-water blast and conical blast, you will able to make these silica materials. In fact, we now made it in even large quantity. This is how they look, highly monodisperse particles. And so it's already 30 minutes. So, and then we also try to understand the formation mechanism of the material. Why I form those spheres? Why not some other shape and morphology? So the synthesis happens. The synthesis was carried out using the templated approach. Templates are molecules. In this case, a CTAB. A quaternary nitrogen and then CS2 CS2 time. The blue ball is a quaternary nitrogen. Zigzag line is a CS2 CS2 up to 16. So polar, non-polar, we added them into the solvent. They form these lamellar phases because we are using high concentration. Then we add one more molecule, pentanol or hexanol. These are called co-surfactant, which stabilizes these interfaces, make them rigid and stable in the solvent. And then we realize that these are not floating flat into the solvent, but they are in the form of a droplet. We call them bicontinuous microemulsion droplet, because it is a microemulsion, because it has this cyclohexane or a xylene and water, two phases continuously mixing. So bicontinuous, and these are the droplets. And these droplets are not the nanoparticles. Actually, these are the droplets made up of water, CTAB, and xylene. And these are like a reactor. And in the channels that you see, we can grow the silica. So by tuning the size of these droplets, I can tune the size of the nanoparticle. We can keep them away, you get smaller particles, or we can force some of them to merge and increase the droplet size. And if you get a bigger droplets, you will be able to get a bigger silica nanoparticles. So that's how we were able to tune the sizes as well as the uh, other thing like morphology and yes, material which we invented in 2010 or 11, now being used by more than 150 group worldwide. for large number of applications, not only in catalysis and CO2 mitigation, but in drug delivery, sensors, energy storage, energy harvesting. So this is like a base material which you can convert into, this is insulating, silica is insulating, but you can convert that into semiconducting, metallic, hydrophobic, hydrophilic, you can put a drug on it, you can functionalize with enzymes, right? There are several possibilities with one single material, and that's why it is used in large number of applications. And we ourselves also filed several other patents in recent times. So now how do I use this for CO2 mitigation? Only capture and storage, not the conversion. So there are two ways to capture the CO2. One is you capture the CO2 from the flue gas that is coming from the chimney, which is say around 15% of the CO2 with a temperature that can be brought down up to 75 degrees Celsius. And there is but then one can ask, why do I wait until the CO2 comes out of the flue gas from the chimney? Can I capture the CO2 right where it is produced in the reactor? Maybe cement industry or a catalytic industry. This is more feasible in a catalytic industry, where in the catalytic reactor you can keep some material which will keep capturing the CO2 as soon as it is produced. But only thing is, these process happens at a very high temperature, 500 to 700 degrees Celsius, and very high concentration of the CO2. Then you need a material which should be stable at that high temperature and still capture the CO2. And there is one such a material, it's called lithium silicate, Li4SiO4, which reacts with CO2. It's a typical chemical reaction. Li4SiO4 plus CO2 gives you Li2SiO3. This is called lithium orthosilicate plus lithium carbon. So this from left to right, it's the CO2 capture. But then once you capture, you want to take it and put it in a cylinder. You reverse the reaction by simply changing the gas to nitrogen at the same temperature. Then orthosilicate and carbonate react together to get you lithium silicate, and the CO2 gas you capture into the cylinder. But because the reaction temperature is very high, most of the lithium silicate reported in the literature was not stable. Within a few cycles, even 2-3 cycles, they used to lose their capture capacity. So we wanted to make something better. So idea was to then convert the DFNS into lithium silicate with a morphology like DFNS. That was the hypothesis. Obviously, that doesn't work. DFNS breakdowns in presence of lithium nitrate at 650 degrees Celsius. It is stable otherwise up to 800 degrees Celsius, but in presence of lithium nitrate, no. And we were never able to make lithium silicate like DFNS. But what we got is some sort of a degraded DFNS sphere with the sheets, and these lithium silicate nanosheets fortunately also work efficiently to capture the CO2. And I skip this. This is how we capture the CO2, and you see the data. So the first cycle it captures around 25% weight percent CO2. Then second cycle it captures more. Third and fourth cycle it captures around 35% of the CO2. So that's a very good number. That's the number that industry wants us. And it's not only the capture capacity that is important, it's also kinetics, because gas is coming through something, then you want to really capture it as soon as the material sees the gas, sees the CO2. So that's the kinetics, right? It's the residence time of the gas will be very less onto the solvent. So you need to capture very fast. So you can see the kinetics of the CO2. It's like a first initial kinetic. So within a minute, it captures around 22% of the CO2, which is again a good number. And I will skip the more technical details to show some other examples. And what you may ask is, the lithium silicate has lithium, and lithium, we all know, we are already struggling with lithium ion batteries, right? We were trying to find out alternatives to lithium ion batteries because we know there is a shortage of lithium. We tried to replace the lithium with sodium or potassium or magnesium. None of them work. Lithium is very small in size and has an excellent mobility. That's why it works. Other doesn't work. So then the process is unstable ideally. But how do I make it stable? How do I make it sustainable? Another way of making it sustainable without replacing lithium is I keep using the lithium, maybe for 100 cycles, 200 cycles, thousands of cycles. Then the overall cost of the process will be low, right? Because I'm using the same material to capture large amount of CO2. And that's what we showed here. We showed that one can capture the CO2. At least we tried up to 200 cycles, which means around 100 days or maybe 150 days. It takes like around 12 hours or more than that to have one complete experiment. So and you see it's very stable. It looks like very similar, right? But you zoom in, you will see some changes at the top, But otherwise it looks like a very constant CO2 capture ability of the material, indicating that you can use it not only for 200 cycles but many more, maybe thousands of cycles. So that will make the process sustainable. Okay, I skip this part. So this is another material which is also CO2 capture sorbent, but this captures the CO2 at a lower temperature, 75 degrees Celsius. This is a post-combustion CO2 capture where you capture the CO2 from the flue gas. But as I said, capture is a temporary solution. We have to do it because we don't have a permanent solution yet. We have to capture and store. But the permanent solution is converting the CO2 to chemicals and fuels. And I already told you that CO2 is a stable sp hybridized molecule. You need to put lots of energy and you need to develop the catalyst to reduce the activation energy barrier, make it kinetically favorable also. And how do I do it? So uh, So the idea here was to develop a material which will not only behave like a catalyst, but which will also harvest the solar energy. Because I said it needs lots of energy, so can I take that energy from the sun? So can I develop one single material which will not only capture the CO2 and convert into fuel, but the energy required is also taken care by the same material. It harvest the solar photon, convert that photon to say electrons or a heat, and then entire system works together. So we decided to use the plasmonic properties of the gold to harvest the solar energy. The gold is shiny yellow color, the bulk gold, that the jewelry and everything that we wear. The reason is the electron cloud on the gold surface, metallic gold, reflect most of the light. Some portion of the blue light it absorbs. Whereas when you go to the smaller size, not smaller, the nano size of the gold nanoparticle, then the electron cloud no more reflect the light, but it start resonate. It resonate with the light at one particular wavelength, and then it absorbs that wavelength of the light, and that's why you get a different colors of the gold by simply changing the sizes. So skip this. So what we wanted to do is we wanted to make a material which absorbs entire visible spectrum. In general, if you take a gold nanoparticle, the absorption spectra is this blue line. It absorbs around say 560 nanometer and a very weak absorption in other wavelength. What we wanted is this dark blue line, a broadband light absorption, which absorb all visible and even near IR. So that means I'm able to harvest large amount of solar energy, which I can use for some other for catalytic application. And how do I change the light absorption properties of the nanoparticle? In this case, gold. Two ways. One is by changing the size. If I change the particle size, you see 9 nanometer absorbs around 550, 560, whereas 99 nanometer absorbs around 600. So that way we can tune. But what is happening? The light absorption lambda max is changing from one wavelength to another wavelength. It is not becoming broad. So simple particle size change will not help. Then there is another concept called the interparticle distance tuning, where I bring the gold nanoparticle closer and closer, right? And it's more like a pi conjugation in your aromatic ring, where these pi electrons, uh, form the ring, and the light absorption can happen at even a lower energy. Exactly same thing, where when you bring the gold nanoparticle closer and closer, the electron cloud on the gold nanoparticles start interact with each other, called plasmonic coupling, which allows you to then absorb broadband light. So we decided to make that, and we use this cycle by cycle approach, where we first took a silica loaded with the gold seed, then we added another batch of a gold precursor in this first cycle, third cycle, fourth cycle, and you see now gold particles are coming closer and closer. We don't know what is the best distances between the gold nanoparticle that will allow us to absorb broadband light. So we decided to make the material with the different gaps and then find out which one is the best. So that's why we made C1, C3, C4, C6. These are the representative, we made more. And these are the TM images also indicating that when you go from C0 to C1 to C3, C4, C6, the particles are coming closer and closer, and in C6, they connected with each other. And this is very interesting data. Now you see C0 is the gold nanoparticle supported on silica. This is the color. C1, again a gold nanoparticle supported on silica, but the color become dark. C3 again darker. C4 is nearly is black, and C6 is also black. It's still a gold. There is no change in the oxidation state. There is no doping, no functionalization. but color becomes black because now it absorbs nearly all the visible light spectrum and of the solar light, and that's why it becomes a black. The reason is, as explained, interparticle plasmonic coupling as well as particle distance. Spectral signature, you can see here. This is the blue curve is typical gold nanoparticle, but when we tune the gaps between the particles, you see now they become light absorption become broader and broader. So that means now I can harvest almost all the photons that comes from the sunlight. And now then there is this theory that once photon is absorbed and when there is a damping of the energy on localized surface, the electrons in the Fermi level of the metallic gold goes to the excited state, by DD or SP to D transition. And think like electrons at higher Fermi level. So these are called the hot electrons or energetic electrons. And then I can transfer these electrons to the CO2 molecules. And then now CO2 becomes reactive. The problem with the CO2 is very non-reactive. But once I add the electron and create a radical anion, it becomes reactive. And then I can add H2 or a proton or some other molecule into it and convert CO2 into different chemicals. So I skip this part, and I will directly show you the results. Yeah, here CO2 plus water, DPCCX is your black gold, and visible near IR light is your sunlight. So ideally, water is free, CO2 is free, sunlight is free. Only you need to make a black gold. You mix all of them, expose with sunlight, and you can convert CO2 into methane, right? And the data, this 1.5 micromole per gram is 10 times better than a normal gold particle. So clearly indicating that the black gold is better in terms of catalytic activity and in terms of harvesting solar energy. And the idea is this, that you will have some sort of a catalytic reactor in your car, which is activable by the sunlight. So I put it's a crazy idea, but one day it may be true, that you will have a tank of CO2 in your car, and then you pass the CO2 into your catalytic reactor, have it exposed with the sunlight, CO2 and the water, and CO2 converts into methane. Methane is your CNG. You burn the methane, dry your car. Car is just example, any engine ideally. And once you burn methane, you get CO2 back. And don't let that CO2 go into the environment, but circulate it back to the catalytic reactor, right? And then again get the methane. You see a cyclic economy, cyclic carbon cycle, where ideally once you fill the CO2, you will never able to fill the fuel again. So if this is feasible, you can see the reaction is possible. CO2 plus methane is possible, but obviously this need to be done at a very a dramatically great efficiency, the kinetics, the productivity, and this is where the science is lacking, and this is where the fundamental research is needed, where I can really develop a catalyst which is good in light harvesting, which is extremely fast in converting CO2 to methane, and it converts large amount of CO2 into methane. The drawback here is, if you look at the y-axis, the methane yield is 1.5 micromole per gram, which is very poor, right? This will not help you to drive your car. But if I can make that to say 1500 or 1.5 moles of millimoles of or something like that, and very fast, say in 10 minutes or less than that, those numbers can vary. And then this dream is feasible, and that's where the role of a chemist can come in, right? Where you will maybe one day have a car which will run by the sunlight and the catalyst and water and CO2, and it's all how we develop the catalyst, how we use the chemistry, organic chemistry, nanochemistry, inorganic chemistry, analytical chemistry, chemical engineering. Okay, so I showed you this, right? The drawback here is the y-axis. The value is only 1.5 micromole per gram, which is very poor. And the amount of CO2 that is there in the environment is around 3,200 gigatons. Huge, huge, huge amount of CO2 is there. So the value that I showed has no meaning. It's negligible in front of this. So if we really want to develop, really want to combat the climate change, what we need? We need a dream process, a CO2 conversion. What should be our dream process? It should happen at ambient temperature and pressure. But I already told you CO2 is very stable. You have activation energy barrier. So why will it happen at ambient temperature and pressure? How do I make it happen at ambient temperature pressure? You can by developing a catalyst which will bring down the activation energy to the lowest possible, right? So that's the first dream at ambient temperature and pressure. then without any external energy, right? That means I don't need to put electricity, even not a sunlight. It should happen using the sun and the energy that is there at room temperature. And water as a hydrogen source. You don't, because CO2, you need to add hydrogen or a proton to convert into methane or methanol or other. So where do I get that hydrogen? If you get hydrogen again from the fossil fuels, that's what we get now in the cylinder, then it has no meaning. It produces huge amount of CO2. So I need to get a water, I need to get a hydrogen from water. So water as a hydrogen source. And then the most important thing, the catalyst that we are going to develop has to be cheaper, has to be readily available. Right now, the catalysts are platinum, palladium, rhodium, even I showed you a gold. These are all expensive. They are vanishing. So we can do a research to understand the science and fundamental understanding of the mechanism, but at one end of the day, we need to use the material which are inexpensive and abundant. Right, so this is how the process should be, and this, if this happens in the next 5 to 10 years, or maybe next year, who knows, then this will solve our problem, at least contribute to combat the climate change. And this is what we observe. It's exactly what we recently find out. Obviously, there is one catch that I will tell you, but before that, if you look at this, CO2 plus water, you take a CO2 and water in a conical flask. In fact, you take a water, bubble the CO2, and have some magnesium powder in that water. It will convert all the CO2 into methane, methanol, formic acid, hydrogen, and basic carbonate. Right? And magnesium basic carbonate is nothing but a green cement. So you can ideally convert the CO2 into different chemicals and fuels like hydrogen and the basic carbonate at room temperature. It works at room temperature, atmospheric pressure, without need of any extra energy, no light, no electricity, no heat. What it really means is the energy that is there in the reactor. The room temperature also has some energy, right? So that is enough to carry out the reaction. And just using that, no external hydrogen is required. And we tested even the seawater. You don't need a drinkable water. You can use the seawater and it also works as fast as the normal water. And the magnesium is the fourth most common element in the earth. After iron, oxygen, and silicon, magnesium is 30% of the earth mass. So it's abundant in abundantly available. Give me a minute. Don't disturb. Oh, sorry. I'm doing it also. Sorry, I forgot. Hello. Yes. So sorry for the disturbance. Um, so magnesium is also available in the easily available naturally, and the process is all easy. It happens at a room temperature, atmospheric pressure. Only problem now that there is a competitive process. There are two reactions in the same reaction. You see CO2 converts into methane, methanol, formic acid. Perfect. That's a catalytic conversion of CO2 to different chemicals. But at the same time, CO2 and magnesium, water reacts with magnesium to produce magnesium basic carbonate. And then at one particular point of time, all the magnesium get converted into magnesium carbon, and the reaction ends there. It's no more, because the magnesium is not there in the reaction, so the catalyst become part of some product. So overall reaction is not catalytic. The CO2 conversion is catalytic, but overall reaction is non-catalytic, and that is the problem, and that's where we are working on. But even if it is non-catalytic, we should skip this technical details. We showed that it is possible to make this process sustainable. So 1 kg of magnesium gives us 2.43 liters of methane, 940 liters of hydrogen, 3.85 kgs of basic magnesium carbonate, and small amount of methanol and formic acid. And basic carbonate is a green cement. Why I say green cement? Because now I am producing the cement by taking the CO2 in, whereas in general cements are produced by emitting large amount of CO2. Cement industry and steel industries are to blame. They are the real villain of the climate change. But here we are doing other way around. And magnesium is abundant in India. It's very cheap, 285 rupees a kg, 45. And what we realize that you don't need to have magnesium nanoparticles. Magnesium powder also is enough. And basic carbonate is also expensive. And then you can see the process sustainability. 1 kg of magnesium can be brought in with 700 rupees. Basic magnesium carbonate is expensive, 2000 rupees a kg. And you see now, if you start a company, you will be rich. So those who are only looking for a who wants to do a chemistry MSc or a PhD just to get a job, no need. You don't need to always look for the job. You can be a owner of the industry and you will give the job. So chemist doesn't always need to look for the job. They can be the job giver, right? And you see how a simple research can. Obviously, there are some challenges here. Otherwise, I could have started the industry. But we're trying. We're trying, and maybe we will able to. We will succeed in this. Okay, we also produce the hydrogen here, and you see amount of hydrogen that we produce. If we don't add the CO2, then the hydrogen is around, just a 2.24 liters. But if you bubble the CO2 in the water, then hydrogen is 940 liters, 420 times more hydrogen. Huge amount of hydrogen, and there is a chemistry again behind it, that why we produce more hydrogen. It helps magnesium to react with water faster and in a more efficient way, and that's why you produce more amount of hydrogen. This is more futuristic, where we showed that magnesium process can be used even at Mars. We know Mars has 95.32% of the CO2. It has a water in the form of ice. You can use the sun energy to melt the ice into water, and then you have water plus CO2. And recently, this is Nature Geoscience 2019 paper, where they observed that there is a huge amount of magnesium on Mars. So use the magnesium and react with CO2 and water, you get a methane, and that's what you need. Methane is the energy, right? So these are called the solar fuels, where you are storing the sun energy in the form of a methane, and you can then go and come back from the Mars. Just fun. Right, so this is the you can do the same thing on Mars ideally. Obviously, there are different tests that is required, like temperature and the gravity and other things. Okay, so I think my time is already up, 4:51. Maybe I take 4 5 minutes more, 2 to 3 minutes more. Other than CO2, the other problem that we're facing is the plastic waste chemicals. This is how the India is, right? We have plastic everywhere. Maybe Mumbai is cleaner, but in general, you see plastics everywhere because plastic is cheap. So we buy, we throw, we buy, we throw. So again, this is more a societal problem, not a scientific problem. If we decide not to throw, then plastic can be our friend, but somehow we like to throw rather than use. Until the society changes its behavior, what chemists can do? Chemists can collect, now somebody else can collect, but chemists can convert these plastic into useful chemicals, right? Plastics are made from different molecules. It's a polymer. So can I reverse the reaction, and can I convert all the waste plastic into chemicals? And by the way, the plastic is not only lying on land, on the surface of the earth, but that they are also in the environment. And when there is a rain, the plastic, microplastics become part of our water body. And then you are ideally drinking the plastic. Majority of must be having it. Even your veg, there are ways where plastic can go in. So what is the best way? What chemists can do? We can convert back these polymer into a basic chemicals, right? Alkanes, alkenes, and then again use these chemicals to build to generate more plastics. How do I do it? There is a simple way: you heat and they degrade. But then it takes very high temperature, around 400, 500 degrees Celsius temperature, to degrade them back to the chemical, and you get less alkanes and alkenes and more coke. And then any process need to be sustainable, right? If you have a 10 rupees plastic bottle and you want to put 20 rupees to recover the chemical, no one will do that. So what we have to do, we have to develop a process where I can convert the plastic to basic chemicals at a lower temperature, possibly room temperature, if you can do that. And that's where one of my students came up with this acidic material, acidic aluminosilicate, where you replace some of the Si from SiO2 network with aluminium, and you get a silica aluminate, which has a strong acidity and porosity, and which allowed us to then degrade the plastic at a lower temperature, say around 100 degrees Celsius lower temperature. So this is like this one is around 450. The plastic carry bag needs around 450 degrees Celsius temperature, but using our catalyst, then it needed say around 350 degrees Celsius temperature, 100 degree less, right? So that was the improvement. But again, I'm just trying to give you the fundamental research and the real application. Can I use this process now to degrade the plastic? No. 450 to 350 is a good improvement, but that is not sustainable. We need to go say 200, 100. Then how do I to make the process sustainable? Then that means I need to provide less energy to degrade the plastic to get the chemicals. That process is economical. How do I do that? Again, I need to go back to the materials design, find out how do I make my material even more reactive, even more porous, right? So that I can degrade the plastic, say at 100 degrees Celsius or 150 degrees Celsius. Once I achieve that, again you start your industry, right? Again you can start degrading the plastic and selling the chemicals and become rich. So again, chemist can do that, and chemist can become a job giver rather than just looking for the job. Okay, with that, I like to conclude. I showed you the use of DFNS as a new catalyst support. I did not show you about the defect part, but I also showed you the use of solution phase synthesis to make these black gold using the concept of plasmonic coupling, which allows you to create either hot electrons as well as the heating, which can be used to convert seawater into drinkable water. And then I also showed you how to capture and convert CO2 using water and magnesium, and capturing the CO2 at high temperature using lithium silicate. And in last slide, I showed you how to convert waste plastic into useful chemicals using highly acidic solid amorphous zeolites. With that, I like to thank my group, Sushma Raul, Ayan Maiti, Rajesh Belgamwar, Saidev Singh, Sushma Kundu, and Rishi Verma. They are all from different parts of the India, so it's like a real India. And then my collaborator Ayan Datta from ICS, Sudeep Chakraborty from HRI Allahabad. Both of them help us for computational support. CP Vinod for XPS and Professor Oliver Lefon for solid state NMR. And majority of our funding comes from Department of Atomic Energy, say 99%, and then there is a support from Indo-French Cepicra, Shell Industries, DSDBT Mission Innovation, and recently Hindustan Petroleum and BASF company. With that, I like to thank you very much for listening to me, and I'm more than happy to answer any questions that you have on basic chemistry or applied or anything that you like to ask.
Thank you, sir.
Yes.
We'll have the question answer session now.
Yes.
Yeah, we'll start with the question answer session. Thank you, sir, for the excellent coverage. The first question from our student participant is actually not a question but a cute complaint. If you allow me to, his complaint is, with some scientists and researchers, he says knowledge of science is misused to change the climate unnaturally. Like last time in month of May, sudden rainstorm and thunder happened. So there are scientists on international level doing the artificial cloud bursting. Shouldn't this all activities causing disasters be stopped?
I have no idea what he's referring to, but in general, scientists are there to help the society. They're like any part of the society, they will always have some crazy people. But I don't know what he's referring, he or she is referring to. That is, one has to read what they wanted to do, and I don't think the simple experiment of a cloud bursting will suddenly have a heavy rain in Mumbai. This thing is not that fast, right? Like you do something right now and something happens. Climate change is a slow process that is already happening from several years now, several decades. So I don't think by some experiment, even if they are wrong or right, you will have such a dramatic impact on our environment.
Okay, sir. We move on to the next one. The second question is, can we use any organic macromolecules for carbon dioxide absorption instead of inorganic materials?
Yes, like see, there are lots of porous organic polymers or metal organic framework. There are different organic materials that can also capture the CO2. Even organic molecules like amines can capture the CO2, right? So that is all very much possible. Now, what will you choose? It's not about inorganic, organic, right? Guys, come out of these. This is we divided the chemistry into inorganic, organic, analytical, blah blah blah, just to have a better learning. But chemistry, if you really want to be a master, you really want to learn, then mix them together at the end of the day and think at a bigger level. So what material shall I use to capture the CO2? What should be the property? It should capture a large amount of CO2. It should capture very fast as soon as it sees the CO2. As soon as the CO2 touches the material, it should capture it, right? The kinetics should be fast. And the third and most important, it should be stable. I should be able to capture for large number of cycles. It should be stable at different environmental conditions, different temperatures. So there, inorganic silica, the inorganic material fits better as compared to organic molecules. Not all, there are stable metal organic frameworks which can also be used. But you can again imagine breaking the CC bond, right, or a CH bond or a CN bond will need lower energy than breaking SiO-Si bond, right? The inorganics are always stable. So in that sense, you will have a better stability. And that's why most of the time you tend to use the inorganic material.
I think you have answered it. Yes. We move on to the next one. The student says that, according to him, very sophisticated instruments are used for carrying out research in nanotechnology. So, is it possible that even carrying out research in the from small institutes also we can get help from the big institutes where instruments are available?
Very good point. Like, uh, this is a more a political thing now, but yes, ideally the research in nano needs a extremely high-end instrument, especially the SEM and TM. But the thinking that if you are in a big institute, that means you will get access is no good. The typical Indian system is very different. Even you have the instrument in your institute, you may not get the access, right? It's a typical mindset of some scientists. They feel like they own the instrument and they never give it to anybody else. So that thing is still continuing, unfortunately. But if we ignore that particular part, yes, if anyone wants to do research in nano, I don't think it is possible in small colleges and even small universities without any support. That will be just a cooking something and saying that and you can always publish in some crap journal. It's wastage of energy, wastage of your time, and you're not going to learn anything. It has to be done under the expert, under the supervisor who really have done the research, and it needs the infrastructure, it needs the facility. So, but then I also agree with you that the question is that is that mean that the nanoscience should be done only to the institute which has all the facility, or can something be done where you do the research in your colleges and those institute which has a facility like TIFR, IIT Bombay, they should open it up. They should run the instrument 24 by 7. You know that the TEM can cost around 30 to 40 crores of rupees, 1 crore a year maintenance. But then why are we using it only for 6 hours or 8 hours a day? It should be run 24 by 7, and then the student can work in day and night, right? And then use it. So this is something unfortunately even not happening even in 2021. So we are still backward in this direction, unfortunately. So that's my take. Well, my group, we ourselves is struggling for that.
Thank you, sir. Sir, next question is, uh, we saw your CV that you have got a lot of awards and fellowships for postdoc, PhD. Can you guide us? How can we try to get the fellowships? Is it that easy or very difficult? Can you put some light for its preparation?
Okay. The questions are very difficult. Huh? Difficult in the sense it's completely different than the science. I mean, so I think the awards and fellowship is all about how hard you work, how talented you are, right? Because they are limited. They are limited. Only few will get it, right? I think. The only way to get all of these is you work hard. If you are in MSc, you get a higher marks, qualify competitive exams, come in top 10 or something, right? That's how you get a fellowship. So and in terms of awards, you do a good science, some breakthrough science, rather than doing some low quality science, publishing here and there, a large number of papers. Rather publish few, do few good project, high quality work. Then there is a probability of getting the awards. That's the best way, obviously.
Thank you, sir. One last question we'll take. Uh, Working with nanoparticles, can it be very harmful to the to us, to human beings?
Yes, that's a very good question. Nanoparticles safety is a concern. Obviously, when you work in the lab, we take all the precautions, right? You wear all the safety gears. We do the thing in the fume hood, and there we don't see risk. Obviously, if you don't take a precaution, it will be always risky, like any chemical. But use of nanomaterials in, say, in a bio application or even in environment application need all these safety studies. But that is generally done if you have something which you plan to commercialize. You will do a safety study and find out whether it impact the environment or the health. So and this is a very important concern, and that generally is done systematically.
Okay, thank you, sir. One more question I think we can take.
Yeah, take
Can
as many
nano?
as you want. Don't worry about the questions. I'm happy to answer them.
Okay, some are quite simple. I don't know. Some are covered in the lecture, but still, I will say, can nanoparticles be used for curing cancer or as medicines?
Yes. So there is this technique called I'm not from the bioscience, but where you have some of these nanomaterial, which if you expose with light, say visible light or IR light, they produce heat. So what you do, you take these nanoparticles selectively to say cancerous tumor and then expose with light. So and these nanoparticles will create a heat around it. It won't dissipate. It will be only on the surface of the nanoparticle, and that will kill the tumor. That's one of the application. Another application is you load the drug molecule, the medicine that you take. You load them onto the silica material or other safer material, and then they act as a drug delivery agent. You have a better delivery of the drug with a better efficiency. And there are several other applications of the nanoparticle in biomedical applications.
Okay, sir. We'll move on to the next question. Which type of equipment is used or required to study carbon dioxide absorption at laboratory level?
Good question. So there are two ways to study the CO2 capture. One is under flow. Like imagine a situation that gas is coming from the chimney, and that gas flow you are passing through a column. Column is filled with the tube. Tube is filled with the solvent, right? So this is a flow process. So this can be done by creating a tube, and then the inlet concentration of the CO2 and outlet concentration of the CO2. That can be monitored by gas chromatogram or any CO2 detector. Uh, the way we do it, we use this, or we have this thermogrametry TGA, which has this balance, and you put a solvent onto the balance and then flow the CO2. So what will happen now? If the CO2 really react with or get captured into the solvent, then the weight of the balance will increase, right? And by subtracting, you will know the total CO2 capture. And these balances are so sensitive that you can monitor the CO2 capture every 10 seconds, every 30 seconds. So you can then get a kinetics. You get a plot of time versus the CO2 capture. And by that, you can calculate the kinetics of the CO2 capture. That's the one way, flow condition. There's another way where I take a tube, take the solvent and keep adding the CO2. It's more volumetric, which is not a realistic way, but people also use this using endosorption instrument, where you take a material, keep adding the CO2 and measure amount of CO2 the material absorbs. These are the two techniques that is required to study the CO2 capture at least a fundamental level, and then you need more afterwards.
One question which is from basic of nanoparticles. A student has asked, what is the main point which makes the properties of nanoparticles so special and different from macro ones? It is only the surface area or something else?
Obviously, surface area is one of the things. So I maybe I need to give us a different lecture on the nanoscience itself. But there are several other things. Like think about I showed you this change of the gold color, gold nanoparticle color, right? That means now the properties, the light harvesting properties are optical property, the property of a material to interact with light is changing. The bulk gold was reflecting, but now the same gold at a nanoscale start absorbing the light. So because now the atomic arrangement is such, the electron cloud mobility is such that it changes the properties. So it's not only the surface area, it's the atomic arrangement, number of atoms on the surface versus in the bulk, the surface energy of the nanoparticles, and you can visualize this way how we make a material, a macro material. You start from the atoms, molecules, and then they self-assemble or condense or polymerize to get a bulk material. Now nano is in between these. So nano is like you are going back. So you are stopping at a higher molecular level. So you start splitting the energy levels now, not like exactly what you see in the atomic energy levels or molecular energy levels, but you still see some individual energy levels at the nanoscale, and all of these together changes the properties of the nanomaterial. Surface area is one of the key factors.
Okay, sir. If any more questions are there, they can post on the Telegram afterwards also. We can pass on to you, sir.
Yes.
I will end this question answer session here. And I thank sir for answering all the questions patiently. It's the time for vote of thanks now. May I request Dr. Vinay Thakur to please come and give the vote of thanks.
Thank you, Hetal madam. Uh, Good afternoon, everyone. I deem it a great honor and privilege to propose the vote of thanks today. First and foremost, I thank our special guest and today's speaker, Professor Dr. Vivek Pulshettiwar from TIFR, who, despite of his busy schedule, and has found time to grace this occasion, which provided an insight to the field of nanoscience and nanotechnology with its application to the environment. I also thank our principal, Madam, all vice principals and faculties of chemistry department for their support, vision and commitment. My special thanks are due to Professor M. Sajid, our head of chemistry department, for his guidance and encouragement in all our efforts. I owe special gratitude to invitees and the student of Mithibai College. Thank you very much. Thank you very much, Vivek sir. It's
Thank you.
over to Hetal madam.
Oh, thank you, sir, for giving the vote of thanks. Before ending the session, I would request Nilesh, sir, to play the national anthem and all the participants to please stand up and salute. Sir, we can move ahead. Nilesh, sir.
जनगणमन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you once again, Vivek, sir. Thank you, all the participants. Please fill the feedback form. The link is already provided in the Telegram group. Okay.
Thank you.
Thank
Bye
you,
bye.
sir.
Yeah.
Yeah, sir. Thanks a lot. Sajid, sir, shall we end the meeting now? Yes, Nilesh, sir. Azam, sir, shall we end the meeting now?
Yes, ma'am. I'm ending now.
Okay. So thank you. Tomorrow we'll be having the 6th day of the webinar and we'll be meeting at the same time. So please remain tuned 10 minutes before 4 o'clock, and the session will be starting at right 4 o'clock. Thank you.